of operations. It turns out it is much easier if I look at the how L and U are multiplied with each other to get write down the L and U matrices, and then we said we kind of followed this Doolittle algorithm, because in which case we said alpha II equals 1, right? We said all the low 1, 0, 0, and I'm not going to stop at 3 by 3 matrix. I'm going to write in general for an n by n matrix. So we have 1, 0, 0, 0, all these things. Then we have alpha 2, 1, 1, 0, all the way to 0. And then in the third row, we have alpha 3, 1, alpha 3, 2, 1, 0, all the way to 0. And then if I keep going, we have alpha n1, alpha n2, alpha n3, all the way to alpha n minus 1, n minus 1, then we have 1, right? That would be the n element. Okay, that is my lower triangular matrix. And then the upper triangular matrix is going to look like we have beta 1 1, beta 1 2, beta 1 3, and so on. Beta 1 n minus 1, we have beta 1 n, right? That is how it's going to look like. Then we have 0, beta 2 2, beta 2 3, all the way to beta 2 n minus 1, beta 2 n. Okay, and then similarly, this all lower triangle is going to be 0. And then finally, we'll have beta n, and this is 0. This is going to be beta n minus 1, n, and the one element before this is going to be beta n minus 1, n minus 1, right? That is how my L and U matrices are going to look like. So I'm going to, I wish to perform operation count from the multiplications that we have done. Now, one thing we realize is that although we wrote the algorithm from these multiplications, the idea is that now if I'm able to count all the multiplications that are there here, which will give me a matrix, then although I have written in a different way, for example, to calculate what is alpha 2 1, I said it is equal to something divided by something and so on, right? So only these multiplications are going to become, or some of these multiplications are only going to become divisions when we try to do it, calculate for each alpha and beta. Okay, but then if I count all the multiplications that are there that we have done in this, that is going to be the same operation count in producing LU decomposition. Okay, I think that's what we agree upon or we understand. Then let me look at column. Okay, that's going to be, I mean, as you remember from the algorithm, we only written beta 1 1 equals A1, right? If this was producing A, then we said beta 1 1 equals A1. That is the only multiplication we have done. We have never multiplied these zeros with these zeros, right? So that's going to basically give you, if I were to write, let us say I proceed with columns in this direction, rows in this direction. Okay, so this is going to be my columns, and this is going to be my rows. Okay, then if I look at the first column, when I multiply with the first row, I'm going to get basically one multiplication, right? That's basically 1 times beta 1 1. Let us say we are still multiplying with that. Then we have alpha, and if I multiply with the second row with the first column, that's going to give me alpha 2 1 times beta 1 1 plus this 0, right? That's not, we are not multiplying with that. So that's basically going to give me alpha 2 1 times beta 1 1, again 1 multiplication, right? And if I look at the third row with the first column, that is also going to give me only 1 multiplication. That means irrespective of whichever row I'm going to look at, I'm going to perform only 1 multiplication as long as I deal with the first column, right? This is going to be all the way to 1 till I reach the nth row, right? It's going to be only 1 multiplication. Now, if I look at, let us say, multiplying the first row with the second column. So I multiply the first row with the second column, that is this one. Then again, this is going to produce, first one is going to be 1 times 0 times this one. That's going to give me only 1 multiplication, right? Because the other one is 0. So we would have only written beta 1 2 in the algorithm. So that's going to produce only in the 1. So this is the first column. This is the second column. This is the second column. So it's going to give me only 1 multiplication. Then if I multiply second row with the second column, that's going to give me 2 multiplications. Alpha 2 1 beta 1 2 plus 1 times beta 2 2. That's going to give me 2 multiplications. And then if I go to the third row with the second column, that's going to still give me 2 multiplications because this is not going to be multiplied. We'll have alpha 3 1 alpha 3 2 plus this 2. So now essentially we'll get 2 multiplications. And then irrespective of how many our rows I'm going to get, look at, it's going to be only 2 multiplications because everything else is 0 here. Below this beta 2 2, everything else is 0. Okay. Now similarly, if I'm going to multiply the third row with the third column, right, then I'm going to get essentially so if I so okay, I've if not with the third column, if I multiply with third row with the first column, right, or first row with the third column, right, first row with the third column, that's going to give me only 1 multiplication, and then second row with the third column will give me 2 multiplications. Third row with third column is going to give me 3 multiplications, and then fourth row with the third column is going to give me still only 3 multiplications because below beta 3 3 everything is going to be 0. That means if I look at multiplications for each of the rows with the third column, that's going to give me 1, 2, 3, and then it's going to continue as 3 all the way here, right? So once you reach to the highest possible value for the column, then it is going to be only that because everything else is zeros below that and you're not going to multiply. Yes, and then similarly, if I continue this process, the fourth is going to be 1, 2, 3, 4, and then the 4 is going to continue all the way down. Similarly, the n minus 1th column, right, is going to give me 1, 2, 3, 4, all the way to n minus 1. And then the last row is also going to be n minus 1, right, because 1 will be 0. Then the nth row, which is the last one, is going to give me 1, 2, 3, 4, all the way to n minus 1. And then the last one is going to give me n. Is this clear?
Oh,
Yeah.
yes, sir.
Hello? Yeah, this is okay. So, yeah. So if this is okay, then essentially this is the, if I were to write this, then this is basically the entire total number of multiplications we are doing for calculating L and U values, right? So what I have done is I multiplied L and U to get A. If we were to calculate L and U separately, these multiplications are only going to become divisions when they go to the right-hand side, or they may have additions and subtractions and so on. Anyway, we are not counting additions. We are interested in counting what are the total number of multiplications or divisions. Okay, so then this entire thing that is in the red square brackets here are the total number of multiplications we have. Now, how do we count all this? Okay, so one way to think about this thing is, now let us say, if I exclude, or if I not worry about this diagonal, right, that is basically this 1, 2, 3, 4. So essentially, let me look at what is there on the above the diagonal. So above the diagonal, what we have is, we have 1, excluding this main diagonal elements, which are basically 1 to n, sum of 1 to n elements. Then what do I, so that means, let me write down what are these elements. So 1 to n is basically, so this is total number of multiplications is going to be, along the diagonal, we have sigma I, where I goes from 1 to n, right? That's what I have. That is basically 1 plus 2 plus 3 plus 4 all the way to n. Plus I have to sum everything that is above and then everything that is below. Okay, that's what I have to do. Okay, so everything above and then everything below is what I have to do. Now, if you look at what is there in the first row here, then what we have is, so this is, how many ones do I have here? I have 1, 1, 1 all the way to n, but then the first one is not included in this one. So this is going to be n minus 1 once, right? That is for the first row. Similarly, for the second row, again, I'm only considering this upper triangular part, okay? I'm only considering this upper triangular part, which is basically included in like this, right? So that's what I'm considering, okay? That's what I'm considering. Then, if I look at 2's, how many 2's do I have? 2, 2, 2, all the way to 2 here. This is going to be n minus 2 2's, correct? Everybody agrees with me? And then if you look at 3's, this is going to be n minus 3 3's. and so on, all the way to I have 1 n minus 1, right? Is it correct what I did?
Yes,
Okay.
sir.
Yeah. Okay. Then if I were to sum this thing, essentially what we have is we have n minus I times I is what we have here. Summed over I goes from 1 to n minus 1, right? If I'm going to substitute for 1, I'm going to get n minus 1 times 1. That is the first element. If I'm going to substitute for n minus 1, that's going to give me n minus 1. That is 1 times n minus 1. That is 1 times n minus 1. So this is the sum of all these multiplications for the entire green colored highlighted portion, right? So essentially that is what this is. Okay, that means I have plus sigma I equals 1 to n minus 1. I have n minus I times I. Okay, that's what I have. Now, let us look at the lower triangular part. So let us look at the lower triangular part. In the lower triangular part, what we have is this much, right? That's what I have. Now, okay, how does the lower triangular part look like? So here, if you look at the lower triangular part, we have again 1, 1, 1, and we have n minus 1 such one. So that is exactly same as this. And then this is 2, 2, 2, 2, and then that is exactly n minus 2 times 2, and so on. So that means this lower triangular part is actually just a mirror image or flipped over version of this upper triangular part, right? I have here, right? In terms of the operation counts. Right, I again have 4, 4, 4, n minus 3, 3 times, and then n minus 4, 4 times, and so on. And if you come to the last one, I have 1 times n minus 1, right? This is exactly the same as what we have done for the top. Although when we have written the initially, it was not looking like it was symmetric as such, but then once we exclude the diagonal, we see that this is kind of pretty symmetric. One is when you go this way and when you go down, right? When you go to right and when you go to down. Okay, that means this is exactly the same sum as we have calculated for the upper triangular part. Then that means this should be equals 2 times whatever we have computed for the upper triangular, right? That is the total number of multiplications and what we have in the LU decomposition. Is it clear before I try to simplify this? Yeah, okay. Questions on this or? Okay, so let's hope it's clear. Then let's look at what is this total count. This is going to be sigma I. Sigma I sum to n terms, n is going to be n into n plus 1 by 2. Plus we have 2 times. This is going to be n times sigma I, where I is going from 1 to n minus 1, minus sigma I square, where I is going from 1 to n minus 1. Okay, that's what I have. So this is going to be n square by 2 plus n by 2 plus 2 times n times sigma I going from 1 to n minus 1 is going to be n times n minus 1 by 2, okay, minus we have sum to n square terms, which is n into n plus 1 into 2n plus 1 by 6, but then we're going from 1 to n minus 1, that's going to be n into n minus 1 into 2n minus 1 divided by 6 is what we have. So if I try to simplify this further, we get n squared by 2 plus n by 2 plus this is going to be n cube minus n square divided by 2 and multiplied by 2, that is gone. And then we have minus, this is going to be 1/3, right? 2 times 1/6 is 1/3. And this is basically going to be n times 2n squared, that's going to be 2n cube. And then we have minus 2n minus n minus 3